Okay, so we're going to call this the last video. It is lecture 2, and we're going to call this 4B, okay? And so basically we're going to cover the Arrhenius equation, and then we're going to cover some reaction mechanisms, okay? So in the last video, we learned that the temperature actually affects the rate of the reaction, and almost always reactions occur faster at higher temperature. And this is quantified by the Arrhenius equation for the rate constant, which is K equals A times E to the anti-logarithm negative E of A divided by R of T. Okay. If you look at this equation, if you increase the energy of activation, this results in a decrease of K. And if you increase the temperature, it actually increases the K. Okay. And you can plot this in a linear fashion. If you this equation actually can be rewritten in a y equals mx plus b format, and in this case your y would be your ln of k and your x would be your 1 over t, and you can plot it on a graph and it should give you a line. Okay, now in terms of this equation, A is the frequency factor, E of A is of course our energy of activation, R is our gas constant, it is 8.314 joules per Kelvin mole, okay, and your temperature is always in Kelvin, okay, because your R is Kelvin mole, right? So another form of this equation is called the Arrhenius two-point form, and I would actually pause the video right now and write this down on your periodic table with all of your equations for this chapter, because you will be using this on the homework. Okay, so in this particular equation, notice that you have 2 T's and 2 K's. Okay, T stands for temperature, K stands for the rate constant. This means that if you do the reaction at one temperature, let's call it T1, you will get a rate constant that's called K1. Okay, if you repeat the same reaction at another temperature, either higher or lower, you will get a different rate constant called K2. Okay. This allows you to solve for the energy of activation if you do a reaction twice, once at a different temperature. Okay, let's look at an actual example of this. Okay, they say that the rate constant for the formation of HI from the elements is 2.7 times 10 to the minus 4, so at 600 Kelvin. So if this is T1, this is your rate constant K1. If you repeat the reaction at 650 Kelvin, T2, you will get a new rate constant, 3.5 times 10 to the minus 2. Let's call this K2. Okay. Based on all of this information, you should now be able to find the energy of activation. Okay. So remember, you've done this reaction twice, once at T1, once at T2, and you've measured the rate constant. Okay. So to do that, we're just going to use the 2-point equation. We're going to go ln. And K2 is going to be 3.5 times 10 to the minus 3. And K1, 1 over M, 1 over S. And your K1 is 2.7 times 10 to the minus 4, 1 over M, 1 over S. Okay? And it is equal to E of A, which we're solving for, over R. R is 8.314 joules over Kelvin moles. And we're going to go 1 over temperature 1, 1 over temperature 2, 650, sorry. Okay. To solve this, I'm just going to do some simplification. If you do all of this, this will come out to 2.56, if you do this in your calculator, equals the E of A over 8.314 joules over Kelvin mole times all of this calculates out to 1.28 times 10 to the minus 4, 1 over Kelvin. Okay. If you take this number, 1.28, and divide it by 8.314, you will get 1.54 times 10 to the minus 5. And your units, your kelvins cancel out. Your units will be moles over joules. Okay, because 1 over joules mole is moles over joules. If I divide this by 1.54 times 10 to the minus 5 moles over joules, and I do this side, same thing, 1.54 times 10 to the minus 5 moles over joules. Okay, this cancels out. My E of A is equal to all of this. Okay, this calculates out to 1.66 times 10 to the 5th power. And 1 over mole joules is really just joules over moles. Okay. If you haven't picked up on this fact already, if you have 1 over moles joules like this is really equal to J over M, right? Moles, right? Just like before when we had 1 over M in your previous video, this equals M, right? Just the reciprocal. Okay, that's part A. Part B is to calculate the rate constant at 700 degrees Kelvin, okay? And again, you're just going to plug in, this is your T2, but now they want you to calculate the rate constant K2. What is K2 equal to? Okay, same equation, ln. Now we're calculating for K2, we're solving for K2, and my K1 is still the same, 2.7 times 10 to the minus 4, and this is 1 over M, 1 over S, okay, is equal to, now I know what the E of A is. E of A is 1.66 times 10 to the 5th joules over moles, okay. I know what R is. R is 8.314 joules over K mole, okay, and I'm going to multiply it by 1 over 600, subtract 1 over, now it's 700 because this is my new T2, okay. So all of this, okay, calculates out to 4.77, okay. My units for that, my joules cancel out, my moles cancel out. I have 1 over Kelvin. So really it's 1.77, and this is Kelvin. So my kelvins cancel out, okay? This actually 4.77 has no units, okay? And I am on this side, ln, I'm just bring everything down, K2 over 2.7 times 10 to the minus 4, 1 over M, 1 over S, okay? Remember, to get rid of the natural log, I'm going to do the anti-log, or the E, okay? That cancels this out, so I get K2 over 2.7 times 10 to the minus 4, okay? 1 over M, 1 over S, okay? Is equal to, E to the 4.77 is 117, okay? And last but not least, I'm going to multiply both sides by 2.7 times 10 to the minus 4, 1 over M, 1 over S. And we'll do the same thing here, 2.7 times 10 to the minus 4, 1 over M, 1 over S. Okay, that cancels out, so K2 equals, this times this together is equal to 3.2 times 10 to the minus 2, 1 over M, 1 over S. So this is an exercise in this equation. This is a lot of math, I realize. So when you're doing this, just be very, very careful and very, very deliberate in terms of how you want to solve for these equations. Let's see here. All right. So the next topic that we're going to talk about is called reaction mechanism. Okay. And the book actually introduces some terms called the net overall chemical reaction, the elementary reaction, the reaction mechanism, and the reaction intermediate. So I'm just going to, I'm not going to read you some definitions. You can read that on your own. I'm just going to show you what each of these things mean. Okay. So if you're looking at this and you're saying NO plus NO gives you NO3 plus NO. Okay. So in a reaction flask, this is happening. Okay. But in the reaction flask, there is some CO. Okay, so when the NO3 is produced, it reacts with the CO to produce NO2 plus CO2. Okay, if you can't picture what is going on, I'm going to draw you a picture here. you've got a flask, okay, and inside it is an O2, NO2, and CO. Okay, so initially this reacts with this. It reacts together, okay, and so initially what forms, the same reaction flasks, it forms NO3 plus NO. There's no more NO2 because that's fully reacted, but there's still some CO hanging around. The moment NO3 is formed, it will react with CO, and it will form NO2 and CO2. And there's still some NO hanging around. Okay? So really, the overall reaction is you've added NO2, okay? And you come out with some CO2 and NO, okay? Let me ask you a question, okay? Is there any NO3 at the end of the reaction? Okay, there isn't. It gets used up, right? It gets formed, and then it gets used up. This is what we call the reaction intermediate, okay? Because it forms, then it reacts with CO, and it gets used up. So it doesn't actually exist in the reactant, and it actually doesn't exist as a product. It just happens to appear in the middle of the reaction, and then it gets used up and is gone, okay? This is called the reaction intermediate, okay? And if you break it down, it really is NO plus NO forming something. This is one reaction, okay? And then NO3 and CO reacting together, and this is a second reaction. This reaction is called an elementary reaction. This reaction is called an elementary reaction, okay? If you break it down, really what is happening is NO2 and CO react together to form NO and CO2. That is your overall reaction, okay? I'm going to use some general terms so that it makes it a little easier to follow along. If I say A plus B gives you C plus D, okay? And I can say that C plus B gives you E, okay? So that means that once C is formed, it reacts with more B and it forms E, okay? So really, this is your reaction intermediate. I don't know if you remember this from Hess's law, but with this you can cancel it out because it gets used up, okay? So really, overall, what is happening is A plus 2B ends up with D and E, right? These are your elementary reactions. These ones right here. This is an elementary reaction. This is an elementary reaction. And this one right here, I'm going to put it in blue, is your overall reaction. Okay? So let's look at an example, okay? You have Cl2, it breaks apart into two Cls, okay? Then that one of the Cls will react to form CHCl3, okay? So another one of those Cls will react with the CCl3 that is formed from the second reaction, okay? So one of these, it gets used up in this elementary reaction. The other one gets used up in the third elementary reaction. Where did this CCl3 come from? It got formed from the second elementary reaction, so that cancels out. Okay, so really, you've got your three elementary reactions. If you add them all up, okay, you should have Cl2, CHCl3 on your reactant side, and you should have your HCl and CCl4 on your product side. This is your overall reaction, or the overall equation. These three are your elementary reactions, and altogether this is called the reaction mechanism, okay? You do need to make sure that the law of conservation of matter is fulfilled, just like any chemical reaction, okay? Now there are three types of elementary reactions. Unimolecular is when you have one reagent or reactant. So you have one thing before the arrow. Uni, like unicorn or unicycle means you have one horn for unicorn or one wheel for unicycle. So uni means one, okay? Bimolecular means you have two reactants before the arrow. Bi, like bicycle, meaning two wheels. Bipedal, meaning you walk on two legs. Bimolecular means you start off with two molecules as your reactants. Termolecular is three molecules. Okay, it is fairly uncommon. Let's look at examples. O3 decomposing into O2 and O, unimolecular. Why? Because it is one. NO2 and NO2, it is bimolecular. And BR, it is termolecular. Okay? They don't have to be the same. We're just counting the number of reactants. So if you're looking at it here, when you're dealing with elementary reactions, the rate has simple predictable forms. When you have one reactant, you have rate equals Ka to the 1. You have two reactants, then it is to the 2. A and B is again A to the 1, B to the 1. 3 A's is to the 3rd. AA is A squared, and then B is to the 1. ABC, A is 1, B is 1, C is 1. Okay. The reason for this is because these are elementary reactions. Okay. What we were looking at in previous videos where we were solving for the order is when you had an overall reaction, right? If we were looking at this reaction here and the overall reaction is this one, okay, it really will depend, the order will really depend on which of these elementary reactions is the slowest reaction, okay? If, for example, okay, this is the slowest reaction, this first one, okay, then really your rate is going to depend on how fast this decomposes. Okay, the rate of this will determine all the entire overall reaction rate. Okay, and so you would say that the rate equals K times Cl2 to the 1. Okay, and in all the other reagents like CHCl3, right, is going to be to the 0. Why? Because really this step is the slowest step. So this step is going to be the rate determining step. How much of this doesn't really matter. You have 1,000,000 of this, it doesn't matter because this is the slowest step. And until this happens and forms two Cl's, this cannot react with the Cl. So really that's why this is to the 0. Okay, if this was what was the slowest step. Okay, hopefully that kind of gives you an idea of why the rate orders were to the 0 or to the 1 or to the 2. Okay, if this, for example, let me just go back real quick. Let's say new situation. Okay, let's say that this is the slowest. These two are the slowest steps, right? Okay, then the rate law would be completely different because it would depend on your CHCl3, right? And then your Cl would be to the 0. Okay, so it just really depends on what is the slowest step. Okay, so keeping that in mind, okay, let's look at the reaction mechanism practice. It says to write the rate equations for each of the following elementary reactions. And so really you're just looking at how many reactants there are. For example, this one, O3 and NO. So you're going to do O3 to the 1, NO to the 1. Okay. If you have a termolecular, this is a termolecular, you have three things, then the rate would be equal to K times I. Now there are two I's, so it's I squared to the N times M, the concentration of M. If you have this is a unimolecular, because there's only one thing. Okay, then the rate would equal K times H2O to the 1. Okay, simple enough to do. Now, because you have lots of elementary reactions to form an overall reaction, often one of these steps, like I said before, is the slowest steps. So that is called the rate determining step. It is the slowest step. Okay, so if you're looking at an example of funnels, okay, you've got three funnels. This funnel is going to be your rate determining step because how fast the water will flow through this funnel will determine how fast the water will flow through overall. Same thing with this, same thing with this. Doesn't matter that you've got these ginormous funnels here. If this funnel is so small, it's going to slow down how fast the water will pour through. That is exactly what is going on, and when you have a fast step or a slow step, your slow step is always going to be your rate determining step. Okay. Another way to look at it is in terms of energy. This is it's going to require this much energy, whereas this step is going to require this much energy in terms of the energy of activation, right? E of A. This is going to require the most energy. This is going to be your rate determining step. Okay? I don't know if this way helps you or this way the funnel picture helps you, but really the rate determining step is the slowest step. Okay? Last but not least, we're going to cover catalysis. It's when you increase the rate of a reaction as a result of a catalyst, and you increase the rate because you're decreasing the E of A, or the energy required to do a reaction. A catalyst is not consumed by the reaction. An example of a catalyst in biological systems are enzymes. And remember, catalyst lowers the energy of activation. Now, because the catalyst binds to the starting material and then it binds to the product, you're going to actually have two transition states. So here you've got your transition state. This is for your uncatalyzed reaction. Uncatalyzed, like normal reaction, okay? And so you went going from here to here. It requires a ton of energy. It requires this much energy to go to the products. If you add a catalyst, that's the yellow line, okay? Notice you have two transition states here, okay? It's because it's going to bind to the product, bind to the reactant, so it's going to bind twice. So there's going to be two transition states. But notice that the energy of activation here is, this is your rate determining step. It's much lower than what it was when it was uncatalyzed. Okay, so it basically lowers the energy needed for the reaction to progress. Okay. If you notice here, what it is ClO3. So Cl plus O3 plus O. Okay. And then it forms ClO plus O2 plus O. Okay. And then it further reacts and it forms ClO2 and O2. Okay. So really, as a practice, okay, if you want, you can try and figure out what is the overall reaction. Okay. So I'll give you a hint. Cl is regenerated in the second elementary reaction, so it is not consumed and can be used again to react with O3. Okay. So this is your catalyst. Okay. CATAL, catalyst. Okay. So I'm going to skip to the next slide here. So another type of reaction of a catalyst reaction is when you have an enzyme. Okay. And an enzyme is when the enzyme is the yellow thing. It binds to your starting material, your substrate, okay? And then it breaks it apart and you get your two products, okay? So that's another example of a catalyst. And notice again that the enzyme stays the same and gets regenerated and it doesn't get used up, okay? Now there are really two kinds of catalysts. There's a homogeneous catalyst, where the catalyst is in the same phase as the reacting species. So a lot of times you add it and it dissolves and it's in the solution. That's a homogeneous catalyst. A heterogeneous catalyst exists in a different phase. Often it's a solid catalyst. One of the best examples of a solid catalyst is platinum. And so oftentimes you'll see a reaction like this and it's all liquid. But inside the liquid there's going to be all this solid floating around. And if you let it stop, and if you stop stirring it, it'll all settle to the bottom. But because you have a stir bar and it's stirring very, very rapidly, you have all this catalyst just floating around. But it is actually not dissolved. This is an example of a heterogeneous catalyst. Okay. And so again, I remind you that notice that when you have an uncatalyzed reaction, the energy of activation is quite high. When you have a catalyst, you have two transition states. And remember, the energy of activation is quite low. Okay. Remember, the energy of activation is always the rate determining step. It's always the out of these two steps here. This is the taller one, so this is your energy of activation. Okay. If in the other one it was, I don't know if you remember from the other picture here. Okay. Here, notice you've got again two transition states. Again, this is the taller one. So in this example, the energy of activation is here. Okay, whatever is the taller of the two, the one that requires the most energy. All right, I'm going to go ahead and stop this video here. This is the end of chapter 13. I'll go ahead and finish the last couple of homework problems on the reaction mechanism. That finishes chapter 13. Once you have finished all the homework, don't forget you do have Canvas quizzes to finish for chapter 13. For chapter 13, there are 2 Canvas quizzes, one from last week and then one from this week. Alrighty, I'm going to stop the video here.